So before I start my talk on fibrations of infinity n categories, I want to take a moment to thank the organizers for giving me an opportunity to speak. And I want to thank you for watching this talk. Okay, let's get into the world of fibrations of infinity n categories. So as I only have 10 minutes, I will mostly review and motivate the results and then state the main results. So for further details, you are more than welcome to check the paper on the archive, or you can contact me or also check the academic website that I have. So one very classical and important construction in the world of category theory is the so-called Grothendieck construction, which builds a functor over C out of every functor from C to Z, and that functor is known as a discrete Grothendieck up fibration, and it recovers all the data of that original functor in the sense that this construction is fully faithful. So using this, we can study functors from C to Z via certain fibrations. For example, if we apply the Grothendieck construction to the constant functor, we just get a projection. More importantly, if we apply the Grothendieck construction to a representable functor, we get undercategories, which are probably the most famous examples of Grothendieck up fibrations. Not only do we get nice examples, but in fact, we even get a Yoneda lemma, meaning we get a very nice correspondence between certain maps of Grothendieck up fibrations and elements in the fiber, which kind of play the role of the values of our fibrations. However, our focus here is mostly on the world of infinity categories, and let us start with infinity 1 categories. So infinity 1 categories can be thought of as a homotopical or weak version of 1 categories. And because composition is often defined in a weak sense, it's often very difficult or sometimes even impossible to directly define a representable functor from some infinity category to the infinity category of spaces, which is what we want. So in this case, we don't actually have a choice. We cannot just study either functors or fibrations and then just correspond them to each other. We really have to focus on the fibrational side. As a result, we now have a theory of fibrations of infinity categories. We have coCartesian fibrations, which help us construct functors valued in infinity categories themselves. And we have left fibrations, which help us construct functors valued in spaces. This has been studied extensively by Lurie in his famous book Higher-Topos theory, but also by Grothendieck, Stevenson, also using quasi-category approach. Real and Verity have studied this using infinity cosmoi. De Brito has studied this using complete Segal spaces. And Ayala and Francis have studied this using exponential fibrations. So there's now like an extensive and good understanding of fibrations of infinity 1 categories from many different perspectives. And as a nice result, if we apply this correspondence between fibrations and functors to the undercategory, we precisely recover representable functors, which is exactly what we wanted and expected. So these fibrations have been applied extensively all throughout the world of infinity categories. So we can use them to define limits and colimits via studying categories of cones or cocones. The first definition of adjunctions of quasi-categories as defined by Lurie was via Cartesian or coCartesian fibrations. We can then use them to study algebraic structures, symmetric monoidal infinity categories, infinity operats, and so on. So fibrations of infinity categories have been proven very effective and powerful in studying the theory of infinity categories. Our goal in this talk is to focus on the infinity n categorical situation. And notice when I talked about infinity 1 categories, I didn't really discuss models too much. That is because although there are different models of infinity 1 categories, they are all proven to be equivalent. And moreover, by now we also have this nice model-independent approach to infinity 1 categories via infinity cosmos. And so it's less of a concern to worry about various models of infinity 1 categories. For infinity n categories, that is not true. There are different models, such as n4 complete Segal spaces, theta n spaces, and computational sets or n comical sets, and so on. And some of those have been proven to be equivalent, but some of them have not. So here we have to be far more careful. It is expected that they are equivalent, but until it is proven, this requires more care. As a result, I will focus on one specific model of infinity n categories, namely n-fold complete Segal spaces, and I want to study Cartesian fibrations in this context. So let us recall that an n-fold complete Segal space is simply a functor from n copies of delta up into spaces that satisfies three conditions. We have a Segal condition that's necessary for composition, a completeness condition that determines the equivalences, and then we need a discreteness condition to avoid additional morphisms. So n-fold complete Segal spaces were introduced by Rasekh and are known to be equivalent to data n spaces. And for n equals 2, they are in fact equivalent to all other models of infinity 2 categories. So let me get to the main result of this talk. For the remainder, let C be a fixed n+1 fold complete Segal space. There's a notion of infinity n coCartesian fibration, which has the following properties. First of all, it comes with a model structure, meaning I can define a model structure on n+1 fold simplicial spaces over C, and the fibrant objects are precisely the infinity n coCartesian fibrations. And that model structure is always left proper combinatorial and simplicial, and in certain appropriate circumstances, it is also enriched over infinity n categories. Moreover, we have a Yoneda lemma for these infinity n coCartesian fibrations, meaning that for every object, we can construct a certain representable coCartesian fibration, which we also denote by a slice, and any functor from that representable fibration into an arbitrary one is precisely corresponds to the fiber over C, which we should think of as the value of that fibration. Moreover, we can prove that a map of infinity n coCartesian fibrations is an equivalence if and only if it's a Dwyer-Kahn equivalence of infinity n+1 categories, meaning it is fully faithful and essentially surjective in the infinity n+1 categorical sense. Moving on to further properties of Cartesian fibrations of n-fold complete Segal spaces, one important property is invariance, which tells us that whenever we have an equivalence of n+1 fold complete Segal spaces, we get an equivalence of the corresponding model structures, which in particular gives us a correspondence between their infinity n coCartesian fibrations. Next, we also have a Grothendieck construction, which, as one might expect, is far more complicated than the one categorical one. However, it does lead to a similar result in the sense that we still have a correspondence between coCartesian fibrations over C and functors from C into infinity n categories. And finally, there's also a universal infinity n coCartesian fibration, and that universal fibration is in fact univalent, which is similar to result for the universal infinity 1 coCartesian fibration. So before I end the talk, let me make two important remarks, one about generalities and one about the future. So about generalities, the result stated here is far more restrictive than the actual result in the paper. In particular, I focused here on the specific model of n-fold complete Segal spaces, but everything I stated also holds for many other models of infinity n categories, such as complete Segal spaces enriched over data n spaces. Moreover, it also holds for more general fibrations, in particular not necessarily fibrations that are fibered over n-fold complete Segal spaces, but for example, fibrations that are fibered over n-fold Segal spaces, which is like a strict generalization. Finally, let me say something about future plans. So we would hope that we can use these fibrations of infinity 2 n categories, and specifically infinity 2 categories, to study limits of two-fold complete Segal spaces, similar to how fibrations have been used to study limits of quasi-categories in complete Segal spaces before. And then building on that, we can hope to use this technique to study infinity 2 topos theory via representable infinity 2 Cartesian fibrations. And with that, I will end my talk here. And in case anybody has any questions, then feel free to reach out to me.